to section 5.2. Now we've done a lot of different powers and we can integrate almost any power of x. Exponents or negative exponents, remember this would be an x to the negative 2. We've got our rational exponents, any kind of fraction. We are on it. Well, there's only one part we don't know, and that's an x to the negative 1 power. 1 over x dx is x to the negative 1 power. So when we integrate that, we add 1 to the exponent, which means we get a 0. Well, x to the 0th power is not a problem. But when you divide by that same power, oh, problem. And yikes. And no, this is not the correct answer. Remember logs. That's the title of our section, logarithms. Well, if you think back about derivatives, when you took the derivative of the natural log of x, you had 1 over x times the derivative of what you were taking the log of, so you got 1 over x. Remember that integration is anti-differentiation? Look how long that word is. That is huge. Okay, anyway, so for integration, we are going this direction. So if we have a negative 1 power, we can integrate. It's just going to give us a log. Now we know how many times we took the derivative and we had just the natural log of x. Wow, maybe 1, maybe 2 times. We always took the derivative of these mammoth big logarithms. So we're going to need to go backwards. And when we go backwards, we're going to look to see what do we have in the denominator. Do we have its derivative in the numerator? If we do, we can do a u substitution, and our answer is going to be a natural log. Okay, so let's look at some examples. Now, when we look at our actual form here, we've got the integral of du over u. That's going to equal the natural log of the absolute value of u plus c. Once again, the plus c because we're back to indefinite integrals. Now, why do we have the absolute value here? Well, when we do logs, we remember that what's inside the log has to be greater than 0. Okay? Well, the absolute value is just going to make sure that it's positive. That absolute value is not going to guard against it being equal to 0. But the original problem has u in the denominator, so the original problem has a domain where u cannot equal 0. So the 0 is taken care of through the domain of the original problem. So our job is just to make sure that the absolute value is taken care of so that we live up to the full-blown u has to be greater than 0. All right, so number one. Number one is very much like our property here. We've got 1 over t dt. It doesn't matter if it's like this, if it's like this, or if it's like this. Either one, you're going to have the natural log of the absolute value of t plus c. Well, like I said, very rarely did we have to take the derivative of just natural log of x. We always took the derivative of the natural log of something more. Probably going to be the same case with differentiation. So when I look at this, I notice I have x to the 5th plus 1. I have 5x to the 4th. When I'm trying to figure out what I'm going to use for my u, I want to look at the powers because I know if I have a higher power here on the bottom, that my lower power is probably going to be absorbed in the du. I also have to keep in mind that the du has to be in the numerator. You can't divide by du. du is something that's multiplied, so that's going to be in the numerator. So that will also help you figure out that if it's a higher power, it's in the bottom, that is u. Hopefully, the numerator will be absorbed with that dx. Okay, so my derivative of x to the 5th plus 1 is 5x to the 4th dx. Sure enough, that's going to be my du. I don't have to do any additional work. Let me change colors. Okay, so when I rewrite this, I have du over u to the 1 power That right there, my friends, is the natural log of the absolute value of u plus c. You can't have a problem with the u in there. If you didn't start with u, you better not finish with u. Don't forget your plus c on all indefinite integrals. Well, that didn't turn out to be quite so bad. Let's see how nasty it's going to get. Okay, well, number 3, I'm looking at that. I have a quantity in the bottom. I have an x squared minus 1, so I can't divide this on my own. I notice I have a higher power in the denominator, so if I let that be my u, will the top be my du? Well, let's find out. You pick u, that way du is already decided. Take the derivative, so that's going to be 2x dx. I don't have that 2, so I'm going to multiply by 2. I'm going to counteract with the reciprocal. So that product is 1. 1 never changes the value. Now, I know what you're thinking. You're thinking, oh my gosh, we have to think about u substitution. Yeah. After we've figured out u substitution will always be an option for us. When I rewrite, u was the denominator, the 2x dx, and remember that dx is actually in the numerator because if you make it into a fraction, it's over 1, so he's up in the numerator with everybody else. So that whole entire thing is du. I get to take my derivative, or sorry, my integral. So I have 1/2 natural log of the absolute value of u plus c. Substitute that u out. That's going to give me x squared minus 1 plus c. Now let's have a little fun with our logarithms because we all know how much fun logarithms are going to be. Whenever I have a number in front of my log, remember your properties. It says that you can take that coefficient and bring it back up as a power. So let's do that. So that gives me the natural log of the square root of the absolute value. Well, let's talk about redundancy. When you have a square root, what's underneath the square root has to be greater than or equal to 0. So I don't really need the absolute value anymore. That square root takes care of everything. Make sure that we are positive, and remember the 0 part is taken care of with the domain of the original problem. So 1/2 times the natural log of the absolute value of x squared minus 1 plus c can be rewritten as the natural log of the square root. Make sure that square root stops. Okay, at that plus c. Oh, so a little bit of log fun. Now on number 4, I can go ahead and divide through on this one. On number 3, I couldn't because I had 2 terms on the bottom. Okay, so I'd have to factor. There wasn't any way to factor, so I couldn't divide on my own. Here you've got 1 term. Let's go ahead and simplify this. Well, t divided by t is 1. 1 divided by t is 1 over t. This whole thing is multiplied by dt. I don't need a u substitution. I can integrate it right as it is. The integral of 1 is t. The integral of 1 over t is natural log of the absolute value of t. Don't forget your plus c on all indefinite integrals. Okay, so dividing on my own made it a little nicer. Okay. Now we have cotangent and we have tangent. And you're probably thinking, oh, Miss Summers probably made a mistake. I don't know why these are on here because everything has been a fraction. Oh, but wait. Oh my goodness, how exciting can this be? Cotangent is cosine over sine. Oh, it is a fraction. Who knew? We knew. Looking at this, now I have a fraction, so I do have the opportunity to find a u substitution. Now, cosine and sine, one is the derivative of the other, pretty close. So how do I know which one's going to be u? U is going to be the one on the bottom. Du has to be in the numerator, so cosine would have to hopefully incorporate with the du. Du cannot be in the bottom. Well, when I take the derivative of sine, that is cosine dx. So sure enough, that whole entire numerator is my du. So I have du over u. When I integrate that, I end up with the natural log of the absolute value of u plus c, which ends up being the natural log of the absolute value of sine. Okay. Super, super pretty. Okay. Now let's look at number 6, because number 6 is very, very similar. Because tangent is sine over cosine. So it can't be much different. Let's check it out. Looks like u is going to be cosine of x. Okay, the bottom, we did the bottom over here. So my du is going to be, oh, the derivative of cosine is negative sine. I don't have a negative, so I'm going to have to put that negative in there. So you're multiplying by a negative 1, multiplying by a negative 1. I have negative 1, and then I have du over u. When I integrate that, I have my natural log of the absolute value of u, which is cosine, plus c. Whenever we have a coefficient in front of our log, we like to take care of that by putting that negative 1 up as our power. So that's going to be cosine to the negative 1 power. Ooh. Cosine to the negative 1 power, well, isn't that the same thing as 1 over cosine? Okay, so we got rid of that negative exponent altogether, but can we get rid of our fraction? Oh yeah, 1 over cosine is secant. Look at that. Goodness gracious, between log fun and trig fun, woo, we were all over that problem. All right, let's look at some more. Ooh, things start to get weird, and you know how I like it when things get weird. Well, when I had cotangent and tangent, I could use this same concept because I can change tangent into sine over cosine, cotangent into cosine over sine, and I can still do the problem. The problem we have is that we cannot integrate natural log of x, okay? We can't, at this moment in time, integrate natural log of x. So if we can't integrate it, we better substitute it out of there. So when you see a natural log of x, he has got to be u. Well, that's okay because we can differentiate it. The derivative of natural log of x is 1 over x dx. Oh my goodness, look at what we have. This is truly a wonderful thing. I really do have 1 over x dx times 1 over natural log. Okay, we have that exact thing right there. So here's my du, and here's my u right here. So when I rewrite this, it looks a lot better than what I just wrote all over. Sorry about that. So I end up with 1 over u du, same thing as du over u. I get the natural log of the absolute value of u plus c. Well, u, what was u? Was the natural log of x? Weird. Natural log of x. Now, if you remember, we actually did a derivative problem. Exactly this problem. Natural log of the natural log of x. You guys freaked out because you're like, can I take the natural log of the natural log? Yeah, you can. And now we know we can integrate to get right back to it. Okay, now, this problem gets more weird, or weirder-er. We're going to do this one in class because I just feel it's too weird for the video. Actually, we just need to kind of review some things, and I want to go old school and teach you like we used to. All right, now we get to number 9 here. Number 9, what's good about number 9 is it's tricky. What's bad about number 9 is it's tricky. I look at this and I remember u substitutions. You're looking for things that are a quantity taken to a power. Well, I don't have a quantity being taken to a power other than 1. But then you have to ask yourself, well, why did they put the parentheses there at all? Well, they did the parentheses there so that you could do a u substitution. If you multiplied this through, you'd have x to the 2/3 power plus x. I couldn't do a u substitution on that, nor could I integrate it.